Hello, I'm Dave. Welcome to my Technical Notes channel. In this video I'll explain how to power your projects using solar power. It's a big topic, so to save you time I've put a video index so you can fast forward to the bits that may be of interest to you. This is the wiring diagram. So to begin with, you'll need a solar panel. A 6-volt panel is ideal for most projects. Various outputs, 1, 3, 10, 12 watts. A charge controller board, which are $1 each, a TP4056 charge controller, a lithium ion battery, an 18650 battery, and connect those to the VIN or VUSB or 5-volt pin of your board. In there I've given an example of a NodeMCU 32 or an ESP8266 Wemos D1 Mini or an ESP32 board. As long as you connect the battery to VIN or VUSB or 5 volts, it will work. I've tested all the boards that I've got here, which is quite considerable, and the lowest input voltage required is 3.9 volts, which is above the 4.2 volts nominal charge of the lithium ion battery. So it's fairly easy wiring diagram there to set up a solar charge controller, or solar input. For the Lowlin D32 or D32 Pro boards with their onboard TP4054 charge controller, you just need to connect the solar panel to VUSB. The onboard regulator and the TP4054 can withstand the input voltage from the solar panel, maximum 6 volts. So that makes it even more easy to set up solar panel on those particular boards. Now let's calculate the power demand for an ESP8266 that is on continuously, either with the Wi-Fi on or the Wi-Fi off, and see how much power it requires. With the Wi-Fi on, it will require 1800 milliamp hours per day. With it off, 600 milliamp hours per day. Or if it was sleeping, 5.6 milliamp hours, or for just 10 seconds sleep, 31 milliamp hours. For the ESP32, similar scenarios, Wi-Fi on continuously, typically 145 milliamp hours, 3000 or 3.48 amp hours per day. With Wi-Fi off, 44 milliamp hour, and Wi-Fi on for 5 seconds then sleeping, 5.6 milliamp hour per day, and then another 10-second example is 31 milliamp hour. So the longer it's awake, the more power it's taking. And on the far right is the typical battery life in days on a 2600 lithium ion battery. So taking those numbers a step further, if you want to power an ESP8266 with the Wi-Fi on continuously, it's taking 75 milliamps at 1.8 milliamp hour per day. A battery would last just 1.5 days for continuous use. If you used a 1 watt solar panel, it wouldn't be enough to power that arrangement. And if you used a 3 watt solar panel, it would. And there's some calculations. Don't worry, because later on there's a calculator I've provided in Excel or OpenOffice where you can vary all these parameters in I think in a fairly self-explanatory way, and do the calculations without having to go through them in longhand. With an ESP8266, predominantly in sleep mode, for 30 minutes, awake for 5 seconds, its demand is 5.6 milliamp hour per day, but with the addition of a 1 watt solar panel providing up to 833 milliamp hours of typical charge a day, it will provide an indefinite power reserve to keep the system running. And again, I'll show you those calculations in detail later. Similarly, to run an ESP8266 with Wi-Fi off continuously, just monitoring something without sending via the radio any data, it requires 600 mAh per day, and a 1 watt solar panel should provide enough power to maintain that operation indefinitely. This is a more graphical representation of the typical charge-discharge cycle per day over 5 days. This is the output of the calculator. So it's an ESP8266 with the Wi-Fi off, running continuously, requires 600 mAh per day, but the 1 watt solar panel will typically, for 5 hours of charging, replenish 833 mAh per day, giving you a 233 mAh reserve. So the system can be operated continuously. The flat tops are when the TP4056 stops charging. Here's a different scenario with the Wi-Fi on, the ESP826 Wi-Fi on continuously, taking approximately 75 milliamps, requires 1800 mAh per day, but that 1 watt solar panel only replenishes 833, so there's a 967 mAh deficit. There's not enough replenishment charge to keep the system running. In fact, it'll last for about 4 days before the battery finally gives up with insufficient capacity. Here's the same scenario again, but this time with a 3 watt solar panel, providing a lot more replenishment charge during a typical 5 hours of charging per day. And you'll see that there is a 700 mAh reserve per day, so it's enough to keep the system operating pretty much indefinitely. Of course, if there are days and days of cloudy weather and the solar panel output is low, the system will eventually go flat, but that's pretty rare in most countries. Next, I'll demonstrate the solar panel and device load calculator. So there are 2 parts to the calculator. If you just want to know what your sleeping device load calculation is, you can just use the bottom part of it. You don't have to use the solar power element. Okay, this is a combined solar charging and battery capacity estimator. At the top is the solar elements, and at the bottom is the device load elements. So this is a Microsoft Excel or OpenOffice spreadsheet. You can find it on GitHub. I've already completed some of the fields, but I'll go through them now. So the first one on the solar panel is what time does the sun become effective for solar charging purposes? 9 o'clock in the morning. When does solar charging end? 3 o'clock in the afternoon in this example. What is its capacity in watts? 1 watt. What's its nominal voltage? You cannot exceed the TP4056 that I'm recommending. You cannot exceed 8 volts input, so the maximum voltage I recommend is 6 volts. In fact, when you look on the market, you can typically only get 6 volt solar panels. Nothing's perfect, so what are the system losses? There's heating losses, there's the panel losses when it gets either too hot or too cold. This is the calculated load current of the device the solar panel is trying to maintain, and this is the battery capacity. And it says for those conditions with that load, the daily demand is 11 milliampere hour, and the replenishment from the solar panel is 933 milliampere hour. So it's in credit all the time. In fact, there's a daily surplus of 922 milliampere hour. And during charge and discharge, the lowest point of discharge reached on this 2600 milliampere hour battery is 2592, so it's barely used its capacity. So there's huge amounts of reserve, and the reserve would be that figure there divided by 0.47. So on the graph, the flat top denotes the battery is fully charged and charging has stopped or is being maintained. The slope downwards denotes the load being applied to the battery. There's no solar at night, so there's no solar charging taking place, and the battery is being depleted. And then when sun rises, the charging of the battery commences until it gets to full, and then it stops charging. And this is hours along here, and it's just a 5-day estimation. It's just to give you an indication of how the solar panel and the battery and the load interact. The second part of the calculator is this sleep calculator. So if you've got a device in sleep mode, and I've said that it's asleep for 30 minutes, it's awake for 10 seconds. When it's asleep, it's taking 60 microamps, and when it's awake, it's taking 75 milliamps. A total demand per hour of 0.47 milliampere hour, and therefore the expected battery life without solar charging is 229 days. And that's borne out by that quite small drop in capacity every day. So this was an ESP8266 at sleep. If I leave the sleep time at 30 minutes and awake time at 10 seconds, and I'll just change that sleep current to 0.011, which is the ESP32 sleep current, 11 microamps, and the wake current is 145 with the Wi-Fi on milliamps. You can see now that the load has nearly doubled, and the duration on battery is now 133 days. And it's still in credit by 933 milliampere hour per day, so there's still sufficient capacity with a 1-watt solar panel to maintain that system fully charged indefinitely. And now I'm going to say that how long is the device asleep for? Well, I'm going to run the ESP32 continuously, so it's never asleep. It's on for 63,600 seconds per hour. Not taking any current in sleep mode, and it's taking 145 milliamps because the Wi-Fi is permanently on. Let's say it's a remote web server or something. Now you can see that we have a deficit of 5,000 milliampere hour, and a deficit of 2,500 milliampere hour per day. So the best thing I can do now is to increase the solar panel capacity to 3 watts. And you can see it's still not quite enough. There is still you can see there is a daily deficit. Let me increase that panel to the next commercially available panel size is about 10 watts. So now a 10 watt panel is just about maintaining the device at continuously on with self-sufficient, and there is a small surplus. So if I try 2 batteries in parallel, double the capacity, that helps. That enables a surplus to be built up of 2,740 odd milliampere hour. So now we know that to run an ESP32 on Wi-Fi continuously, we need a 10 watt solar, 6 volt 10 watt solar panel, and and ideally 2 batteries in parallel, but I'll put that back to 1 battery because it's still sustainable with 135 milliampere hour. The problem comes in winter when you go to, say, sun up is very late in the day. I'll say it's got sufficient energy to start the solar panel charging at 11 o'clock in the morning and only till about 2 o'clock in the afternoon. Now you see that there is no battery reserve, and in fact there isn't enough to keep the battery charged. But if I increase to 5200 milliampere hour battery, there is still sufficient capacity in the system to keep the system running. So you now know that to run an ESP32 during the day with very low amounts of light, and assuming there is always some sunlight, this time between 11 and 1400 hour, with a 10 watt panel, which is quite large actually, at 6 volts, and a 5200 milliampere hour battery, the system can operate and be self-sufficient for about a day, 1 or 2 days at the most, when the sun goes in. So there's an example of using the load calculator and the solar panel calculator. Just to refresh one more time, a typical sleeping ESP32 operating every 30 minutes, asleep, awake for 15 seconds. When it's asleep it takes 15 microamps, and when it's awake it does take with the Wi-Fi on 145 milliamps. On a 5200 milliampere hour battery it's going to last 180 days, and that includes the system losses as well. So it's actually more than that if it was a perfect system, but it's not a perfect world. 2600 milliampere hour battery, it will last 89 days, and that's typically what you'll see in practice. And if I change that to an ESP8266, which is, let's say it's quite high in sleep mode, but in Wi-Fi mode 75 milliamps, that's going to last 160 days. It's much more efficient, if you like to call it that, for battery operations, is the ESP8266. So that was a quick overview of the calculator. If you exceed solar panel volts, it will say so. 7 is the maximum, but you can't buy 7, so 6 is typically what you need to use. That was the solar charging battery capacity estimator. I have an ESP8266 that's outside and running on solar power, and there is the results of the voltage as it's charged and discharged every day by the solar panel. It's a 1 watt 100mm by 60mm panel. So it's just showing you that in practice the results are, as you'd expect, to be very similar. Of course there are variations in sunlight throughout the day, so it's not a perfect graphical representation, but it's actually occurring, and you can see that on my web page if you wish, under the external weather data logger. This is the schematic of the TP4056 battery charger. I've called it a solar battery charger, but it's a lithium ion battery charger. It's got a charge controller with a blue charging LED, a red charged LED, and a battery management, and some inbuilt MOSFETs for controlling the battery charge on off. Without going into a lot more detail, that is its schematic for your edification. In summary then, using a solar panel is easy. The wiring is very simple in my opinion. It's still dependent on the weather. Obviously no sun means no battery capacity, there's nothing to replenish the charge, but a careful selection of the battery and the solar panel capacity can ensure continuous operation. I haven't gone into the details of solar illumination of your location and solar panel conversion. You don't need to, in my opinion. There are only a certain amount of solar panels of standard outputs available on the market, so in practice use one that the calculator indicates is fit for your project. I hope you found this technical note interesting and useful.